The title of this talk is Good Data Structure Experiments Are Rare. Let's jump in. Why do we perform experiments? Well, we want to answer questions about data structures. Is one data structure faster than another? If so, why? And we're asking about algorithmic differences, not engineering differences. So what's the problem with experiments in the literature? Well, here's a typical data structure experiment description. So our experimental system had two Intel i7-4830V3 processors for a total of 48 threads. It had 128 gigs of RAM and it ran Ubuntu 16.04. We compiled all of our code with the latest G++ 6.3 and we used these flags where 03 means we have the highest level of optimization. We ran the standard binary search tree benchmark, so we have 5 3-second trials, and in each trial we pre-fill the tree to contain half of a fixed key range from 0 to 100,000, and then we have 24 threads, do 50% insertions and 50% deletions. You flip a coin to figure out which one to do, and these operations are performed on keys that are drawn uniformly randomly from the fixed key range. So this seems like a pretty reasonable description, right? Well, it turns out that there are a lot of configuration parameters, system configuration parameters, that are really impactful when it comes to performance, but that we don't typically talk about in the literature. And by playing around with just 4 of these configuration parameters, I was pretty easily able to come up with 24 different configurations where we have the same data structure and the same workload. Everything in all of these configurations, all of these results you're seeing, conforms exactly to the description that I just gave you. And yet, we're able to get performance differences from 9.4 million operations a second all the way up to 29.3 million operations per second. And if I ask you, which of these numbers reflects the true performance of this orange algorithm, you're going to have a pretty hard time telling me which one it is. And this problem gets worse as we want to compare two algorithms. So here on the left, the orange algorithm is a lock-free external BST, and on the right, we have a lock-based AVL tree that uses optimistic concurrency control techniques. And so if we want to compare these data structures, well, if you do like an anything goes comparison, I can show that the blue algorithm is 168% faster, and I can also show that the orange algorithm is 84% faster. Maybe we don't do an anything goes comparison, maybe we do a more reasonable comparison where we only compare with the same configuration. Well, it's still pretty easy to find configurations that favor the orange or the blue to varying degrees. So, I mean, which of these comparisons is the right comparison to make? Are any of them fair? Are any of them reasonable? Do they make sense? Am I doing good experiments here? I mean, I haven't told you what these configurations are, so you have no real way to evaluate the information that I'm giving you, and this is exactly what we deal with in the literature. So how do we get good experiments? Well, good data structure experiments should be reproducible. This means figuring out all of the system configuration parameters that are relevant to your performance results and specifying them. So if I have a similar machine, I have some hope of being able to reproduce your results. You want to do apples to apples comparisons, fair comparisons. You want realistic experiments, so you don't want to show that your data structure is faster in some strange contrived scenario, and you want results that are explainable. And when I say explainable, I don't mean you're able to just conjecture some sort of explanation for why you have a performance difference between two algorithms. I mean you should be able to collect real systems level evidence to help you form hypotheses, and then confirm those hypotheses with auxiliary experiments, and then you're really able to explain where performance differences come from. So let's start to look at these principles. You'll notice that these principles spell out R.A.R.E, you know, that's a little bit of a play on words. Of course, these kinds of experiments are rare in the literature, but you know, I want to bring to your attention a lot of the types of problems that I see in published experiments so that you can join me in producing more of these kinds of rare experiments. Hopefully we can make them less rare. So the first of these principles, the reproducibility principle, hinges on all of these crucial configuration parameters that I mentioned. So here is a non-exhaustive list of things that are really important to talk about. In the operating system, you have a memory allocator. You know, do you use the glibc allocator, the standard allocator that comes with many Linux distributions, or do you use a fast, scalable allocator like jemalloc? In the operating system, memory is organized into pages. An OS might use small 4 kilobyte pages, or it might use 2 megabyte or even 1 gigabyte huge pages. If huge pages are used, they might always be turned on, enabled all the time, or the OS might profile running applications, and when it sees a certain allocation pattern, switch from using small pages to using huge pages on the fly. And of course, this can affect different algorithms differently, because only some algorithms can actually produce the necessary sequence of allocations, the necessary allocation pattern. There's thread pinning, which determines where threads can run. So if you let threads run unpinned, then they can run on whichever logical processors they want, and they can hop between different processors, they can migrate. You can pin threads so that they'll run only on a certain logical processor, and if you do so, you have different options. You could pin with a clustering policy so that you try to fill up one socket before scheduling any threads on the next, or you could do a scattering thread pinning policy where you try to scatter threads across sockets as evenly as possible. There's a lot of state in processors, so we have prefetchers that try to anticipate what kinds of data we're going to be interested in next, and load that data into the cache ahead of time so it's ready for us when we access it. In modern Intel processors, there are actually 4 different independent prefetchers that can be enabled or disabled one by one. You can do this in software without even rebooting, so it's really important to understand what configuration your machine's running in. You have hyperthreading, which allows you to run multiple threads on the same core, sharing some resources, sometimes with some nice performance speedup. And hyperthreading has some interesting interplay with thread pinning, because you can pin threads in such a way that you're highlighting or revealing the effects of hyperthreading, or obscuring the effects of hyperthreading. There's also a feature of modern Intel processors called turbo boost, which is really important to know about if you're doing any sort of scaling results or you're studying the scaling of an algorithm. Turbo boost allows a processor to overclock itself, so it runs at a higher clock speed and can perform more work per unit time if there's only one thread running. And some modern versions of Turbo Boost, some very recent versions, can actually have some boost for 2 or 4 threads as well. So at very low thread counts, you may have artificially increased performance numbers that can end up skewing your scaling results, making it seem like an algorithm is scaling more poorly at high thread counts than it actually is. And in the data structure, you also have some important parameters. Do you perform memory reclamation? If so, how do you perform memory reclamation? Do you use the same memory reclamation algorithm for all of your data structures? And when you're actually ready to free an object, when an object has been taken through the memory reclamation process up to the point where it's safe to free it, do you free it to the OS, or do you put it in an object pool and just reuse it? That's important to think about as well. And all of these configuration parameters play into the next point, apples to apples comparisons, because in order to get a fair comparison between different data structures, all of the data structures have to use the same configuration parameters. And the biggest mistake that I see in this respect is that often researchers compare 2 different data structures that have 2 different memory reclamation schemes. And so they're varying 2 different parameters, and then they're making inferences about something algorithmic in the data structure, ignoring the difference in memory reclamation schemes. And this is bad, because if you fix the data structure, in my own experiments, I've seen that varying the memory reclamation scheme can change the data structure's performance by, 2x, 3x, even 4x. So if you want to be sure that the performance difference you're seeing is due to some algorithmic difference in the data structure, you have to fix the memory reclamation scheme. And of course, some other things to look out for. You want to make sure that you avoid subtle differences in the abstract data type. For example, if you evaluate a set versus a dictionary has to keep, in addition to keys, a value associated with each key. And storing those extra values in nodes increases the size of nodes, which decreases the fraction of the data structure that fits in cache, and this can affect performance quite a bit. Similarly, you want to have uniformly excellent engineering practices for all of your data structures, so you're not just measuring engineering differences. And of course, you want realistic experiments. So you want a realistic system configuration. The biggest mistake I see in this respect is researchers don't use a fast, scalable allocator. They use the default glibc allocator, which just does not scale well beyond moderate numbers of threads. And this can unfairly penalize data structures that allocate a lot of memory. And really, there's no excuse not to use a fast scalable allocator. They're trivial to obtain, they're really easy to use, you don't even need to recompile your code. And in practice, in industry, if someone's really interested in a fast concurrent data structure, then surely they're going to use a fast scalable allocator, so we should as well. You want a realistic data structure implementation. This means you have to perform memory reclamation. And in my opinion, if you perform memory reclamation, you also want to perform some free calls to the operating system. You want to release memory to the OS. If you just use object pooling to the exclusion of freeing memory to the OS, then your algorithm ends up with some really undesirable properties. For example, once you hit your peak memory usage, you can never contract the memory space for your program, and that means you're stuck always using the peak memory usage. This is really undesirable in what are probably some of the most common executing environments now. For example, virtual machines, where you have a certain amount of memory that's being shared amongst lots of virtual machines, and memory is sort of a precious resource here. So you really want to be able to contract your memory space. And it almost goes without saying that you can make your data structures as fast as you like, but if you have implementation errors, your experimental results are not worth very much. So you have to really relentlessly ferret out and eliminate implementation errors. And I'm going to spend a decent portion of this talk explaining the kinds of implementation errors that I see in practice. But first, let's return to this task of making this comparison between the two data structures we studied previously. Here I've combined all the data from the two data structure graphs we looked at onto a single graph, and I've unveiled each of the 24 anonymous configurations that we were looking at. And there are of course 4 configuration parameters that go into these configurations. So on the very left we have the memory allocator. At the top we have the glibc allocator, the standard allocator on Linux. Then we have Google's thread caching malloc, which kind of used to be the reigning champ allocator. It's actually been deprecated for a few years now and hasn't been updated much. And then at the bottom we have JE malloc, which in my mind is the reigning champ of fast scalable allocators. This is something that's seen a lot of work by the guys at Facebook, and they use it on a lot of their production systems right now. The next factor is the way that we pin threads. So do we cluster and fill up one socket before scheduling any threads on the next, or do we scatter them across sockets as evenly as possible? The third factor is whether or not we do object pooling to the exclusion of freeing memory, and the fourth is whether or not we do memory reclamation. And it's labeled GC here just so it fits on the graph nicely, but actually it's an epoch-based reclamation scheme. So how can we sort of streamline the task of making this comparison and just deal with this huge amount of data we have using the R.A.R.E principles to guide us? So reproducibility is satisfied or at least helped quite a bit by the fact that I've unveiled what these anonymous configurations are. Of course, in a real paper I'd want to specify what the values of those other configuration parameters I discussed are, but we're at least doing pretty well with the information stored on this graph. Apples to apples comparisons is satisfied as long as we only compare these two data structures in the same configuration, and that leaves us with realism. So for realism, I'm actually going to rule out these glibc results because the allocator clearly doesn't do as well as the others, and as I've mentioned, if you're interested in really fast concurrent data structures, you should just use a fast concurrent allocator. Also, we're only looking at 24 threads here, and if we were going all the way up to the machine maximum of 48 threads, glibc would actually scale a lot worse relative to the other allocators here than we already see it doing. So I'm going to rule out the glibc results. I'm also going to rule out the tcmalloc results, and the reason for this is that if you drill into the code for tcmalloc, you'll realize that it actually doesn't free memory to the operating system. I'm going to rule out the use of object pooling to the exclusion of freeing memory for the same reason, and I'm also going to rule out configurations where we don't do any memory reclamation. That's not very realistic. Now, of all these configurations that I've ruled out, I'm not saying you can't look at these configurations and use them to understand interesting things about the algorithms you're studying. I'm just saying if you're going to pick one or two things to show in a paper, we have good reason to choose these remaining configurations over the other configurations that I've ruled out. And you notice I've left not one but two configurations. We've got these two different thread pinning policies, clustering and scattering. So I think it's really nice to consider different thread pinning policies, or even to consider not pinning threads at all. Not pinning threads is somewhat realistic, but we can learn interesting things from each of these pinning options. So when we cluster threads, since we're running 24 threads and there are two sockets, each of which can run 24 threads, all of these threads are running on a single socket. And with the scattering policy, we're running on 2 sockets. So the difference between these 2 configurations is actually revealing something interesting to us. It's showing the sensitivity of the algorithms to the effects of non-uniform memory architectures, specifically to the cost of transferring data across the bus between the 2 sockets. And in this case, the effect seems to be about the same on both algorithms, but that's not always the case. You can sometimes get performance inversions if some algorithm is much more sensitive to NUMA effects than another. So in the end, after we've kind of reduced our state space to just realistic configurations, we're left with this rather unremarkable result that the orange algorithm is about 1 to 6% faster, which is really not much of a difference. And this is a far cry from what we see in papers that publish small tweaks to their algorithms and say, hey, we got 50% improvement or 100% improvement, and a lot of that is often due to them just looking at unreasonable or unrealistic configurations. So how do we perform R.A.R.E experiments? Here's a flowchart form of my conception of how you do this, at least. So you design your experiment, you implement your experiment, and then you try to discover all of the relevant system state that could affect your experiments. And I've listed a bunch of things to get you started, but maybe there's something else that affects your experiments. Then you run your experiments, and the next step is to perform some really extensive sanity checks. So whenever I implement experiments, it's a surefire bet that I have made mistakes. I've done this for quite a while, many years of running experiments like this, and I still make tons of elementary mistakes when I implement them. So there's an iterative process where I'm running all sorts of sanity checks, everything I can think of, to try to identify and expose bugs all over my test harness and in my data structures. And every time I fail a sanity check, I've learned something really important. I've learned that I've made either a design error, an implementation error, or a configuration error. So what are these? Well, maybe I've made some unfair or unrealistic comparisons, or I have some bugs in my code, or I've engineered algorithms in a way that's unfair to, favoring one algorithm over another, or I've made some sort of configuration error, maybe I've forgotten to configure some parameter, or maybe I'm rerunning my results and I can't reproduce an old result, and something has changed on the machine, and what's really happening is I've got an opportunity to learn about some system configuration parameter that I didn't even know about before that actually has a really big impact. I need to make sure that I'm fixing the value of that parameter and recording what it is. Only once I've passed all of these extensive sanity checks am I really actually ready to look at the results. And when I look at the results, I don't just kind of conjecture reasons for the performance differences I see. I use systems level tools to start to gather performance data about the run. So the CPU records lots of interesting information, or it can be configured to record lots of interesting information about your executions. You can gather all sorts of information with performance counters that are inside the CPU, and you can use that systems level detail to help you hypothesize about algorithmic causes for the performance differences that you see. And then the hypotheses are not what we write in the paper. We want to confirm those hypotheses, test and confirm them by constructing auxiliary experiments that will reveal whether those hypotheses are actually correct. So if we see that some hypothesis is not correct, we re-enter this iterative process of identifying the kind of error we've made, fixing our experiments, rerunning them, passing the sanity checks, and then gathering results and coming up with new hypotheses to explain what we see. And really only once we've confirmed all of our hypotheses and we can explain all of the differences that we see between algorithms and the data, or even the lack of differences where we might expect some difference, are we ready to publish the results. And a nice benefit of performing experiments in this way is that when it comes time to publish your experiments, you're not stuck sort of saying, what can I write in my experiment section? You know what to write. You have a wealth of information, and you have really valuable, interesting things to contribute to the discussion usually. So for the rest of this talk, I'm going to discuss common implementation errors that I actually see in practice in published code all the time, and then I'm going to give you one slide. I'm going to run down my top 10 sanity checks. So let's jump into the implementation errors. The first one I'm going to talk about is test harness overhead. So I've spoken to a lot of researchers who seem to believe that it's basically reasonable to have just about any amount of additive overhead in their test harness, as long as it's applied uniformly and equally to all algorithms, because it's fair as long as we apply the same overhead to each algorithm, right? Well, not really, because it turns out that a certain amount of additive overhead affects different algorithms differently. In particular, if you have a really efficient algorithm with really low overhead operations, it's going to be penalized way more by a fixed amount of additive overhead than another type of operation, which is really high overhead already. It's barely going to make a dent in that high overhead operation. And so you can really get into trouble if you make claims like, hey, our orange algorithm in this worst case scenario is at most 50% worse than our competitor, the blue algorithm. That's the sort of claim that I saw in a paper that inspired this experiment, so I ended up getting the author's code after I was a little bit suspicious of that claim, and I ran the experiments on a similar system. My system, of course, was a little bit different from theirs, so the blue algorithm was a little bit better than, 2x, the orange one, but looking at their code, I found that there was a lot of overhead in their test harness, and by removing that overhead, I was able to blow up this difference between the blue and the orange from 2x to 3x. So this really makes a big difference, and you can really get into trouble if you're making these kinds of statements. Hey, we're only this much worse in this worst case. You've got to make sure that you're being fair with the overheads that you're applying to these algorithms in your test harness. The second thing I want to talk about is the volatile keyword in C and C++. So if you don't know, this keyword informs a compiler that an address might be changed by another thread. And this has the effect of preventing some optimizations that are legal in a sequential setting but are illegal in a concurrent setting. So to give you an example of this, here is a design pattern called value-based validation, which you often see in software transactional memories and in some other interesting algorithms like the lazy linked list and so on. And the way value-based validation works is you have this address and you read it and you store the result in v1, and then you do a bunch of unrelated work and then you reread that address and store the result in v2. And if that address contained the same value at both of those reads, if v1 is equal to v2, then some invariant holds at all times between those two reads. And if not, we say that validation has failed and we return fail and maybe try our operation again. Now, if you don't mark that address correctly as volatile, then the compiler can actually perform an illegal optimization that completely eliminates validation. So here's what that looks like. The compiler reads, says, okay, you're going to read address into v1, then you're going to do this unrelated stuff. And hey, you're not writing to address, you're not changing it, so it should contain the same value as it did before. So I'll just reuse that previous value v1 as v2. Now, in doing that, it's made it impossible for v1 to be different from v2, which means it's impossible to fail validation. So we've eliminated validation. This is totally illegal. It breaks correctness in algorithms that depend on this. So this is bad. We want to make sure that we're using volatiles correctly because it breaks correctness when we don't. And I think the biggest reason that I see for people misusing volatile as a keyword is that they don't understand how where you place volatile in a definition affects the meaning of volatile in that definition. So here are 5 different examples of definitions including volatile. Just imagine that node t is a node struct that has like a key and a value and a left and right child pointer, and we're trying to define the left child pointer right now. And the secret to reading these definitions is actually to go right to left. So in case 1, left is a pointer to a node. In case 2, left is a pointer to a node that's volatile. So the node is volatile here, and the pointer itself, the left pointer, is not volatile. So you'll read this left pointer, and you're doing a non-volatile read, which means you might be subject to illegal optimizations that break your correctness, and then, so that's a correctness bug, and then you also have sort of a performance bug, because once you follow this pointer to reach that subsequent node, that node you reach will be volatile, which means all of its fields will be treated as if it's volatile. So if you access like the key of that node, and in the algorithm you're working on, the key is never updated by another thread, so it doesn't need to be volatile, nevertheless, you're going to be making a volatile access. You're going to pay the performance penalty of making a volatile access. So you've got kind of a correctness bug and a performance bug here. And case 3 is actually the same. It's a pointer to a volatile node, which is the same as a pointer to a node that's volatile. Case 4 is a volatile pointer to a node that's not volatile. And this is what we want most of the time in data structures. We're usually trying to say, hey, I'm trying to, implement this node. I'm trying to say the left pointer might be changed by another thread, so it should be volatile. And so this is what I want in that case. And, just for fun, in case 5, we have a volatile pointer to a volatile node. So this one is correct, but we have the awful performance of accessing that node and then having all of its fields be volatile. So this fourth one is what we want most of the time. And if you look at published code, the author's code for their data structures, published code in major data structure libraries, current commits, the up-to-date code, it's really easy to find misplaced volatile keywords that cause performance problems and that cause correctness problems. It's quite easy to tease out these kinds of incorrect executions. So we have to pay attention to our volatiles. The third thing I want to talk about is checking for memory leaks. So I've advocated for using a fast scalable allocator. JE-malloc is my favorite. A really nice fringe benefit of using JE-malloc is that it actually has a lot of utilities built in for helping you profile memory leaks in your program. So for example, you can run this relatively simple command to profile your program for memory leaks, and it spits out this nice output that says, hey, I think you've leaked about 8.4 megs of data, and you can run this subsequent command to get more information. So when I run that subsequent command, I can actually get a PDF picture showing me the graph that gives me a lot of information about where my memory is being leaked. It looks something like this. I know you can't see this very well, so let's zoom in on a small part of it. And for example, this function trial is allocating 379K of data that's later leaked, it's not freed, and in functions called by trial, there's another 8.08 megs of data that's allocated but doesn't end up being freed, it ends up being leaked. So it's a lot of information about exactly where this memory is being allocated. This is a real example from a real test harness that I had to fix a memory leak in. I thought that the leak was probably pretty inconsequential. It was about 8 megs of leaked data, and in each trial that I executed in this test harness, I'd allocate like tens of gigs of data, so it seems really inconsequential. It certainly didn't seem like it would affect performance very much or anything like that. But it turned out that this memory leak actually masked a really serious algorithmic bug that I was really happy to find. So maybe this can serve as a cautionary tale for you. I would really recommend that you relentlessly track down all memory leaks in your program. There's another really good tool for finding memory leaks. It's called valgrind. Really excellent program for doing this. It doesn't just help you track down memory leaks, it also helps you find all sorts of other bugs. Like for example, it'll tell you, hey, I think you walked over the edge of your array, I think you accessed some uninitialized memory, oh, I think you branched on some uninitialized memory over here. It'll give you for each of these cases like line numbers where it's happening. Here's what the output looks like when you find leaked memory. Here it says, hey, you allocated 154 objects at line 307 of snapcollector.h, and here's the rest of the stack for the, that was active during those allocations, and those ones were leaked. So I've gotten an enormous amount of information about precisely where my memory is being allocated when it's subsequently being leaked. The only real downside to using valgrind is that your program's going to run probably 100 times slower. That's not really a problem because you just disable prefilling of your data structure and then you work with sort of a smaller experiment, but that's okay, you can do that. I would really highly recommend running all of your code through this and making sure you pass it with no errors. So the fourth thing I want to talk about is false sharing. You might know what false sharing is already, but let's just get on the same page. So roughly speaking, the memory in your computer is divided up into 64-byte cache lines, probably if it's a modern Intel or AMD system. These contain 8 words if it's a 64-bit system, and if thread 1 wants to access a word of this cache line, word 2, it wants to read that word, it'll load a copy of this cache line into its cache in shared mode. If thread 2 wants to read a different word in that cache line, word 7, it will load also a copy of this cache line in its cache in shared mode. Now if thread 2 wants to write to W7, it's going to switch its cache line copy from shared mode to exclusive mode, and in doing so, it's going to invalidate thread 1's copy of this cache line and evict that cache line from thread 1's cache. So we have memory contention here, even though we don't actually have data contention. They're actually operating on different words. And the unit of memory contention on modern Intel processors is actually 2 adjacent cache lines, or about 128 bytes of data. And that's because every time you read or write to a cache line, the adjacent line prefetcher loads the adjacent cache line as well. So false sharing happens in data structures, it also happens in test harnesses. I'm going to talk first about false sharing in the test harness, and afterwards we'll see false sharing in the data structure. And the thing I want to point out is that eliminating false sharing in the data structure by padding data is a little bit of a double-edged sword because it's really easy to accidentally destroy your cache performance, as we'll see. So the way that I reveal false sharing in the test harness is typically by performing sanity checks. One of my favorite sanity checks for doing this is to perform a read-only workload, 100% search operations on empty data structures. And what I do by using empty data structures is I remove all the nodes of the data structure from the picture, except for maybe the head or the root node, and we're really analyzing the interactions between data in the test harness and data in the test harness with the head or root node of the data structure. So here's an example of me running an experiment just like that on a real test harness with lots of data structures where I really had to fix false sharing problems and some other problems. So here I have 6 different data structures, and for each data structure I have 4 or 5 different flavors of that data structure. And if you're curious, the different flavors are different implementations of range query algorithms. And for the most part, those range query operations don't affect the way that searches are implemented. So a lot of these algorithms, flavors of each algorithm, have the same search code and the same data layout. So I would expect that basically all of them would have uniformly very high performance, because we're talking 100% searches in empty data structures. They should all be able to do hundreds of millions of operations a second. And for example, here, the lock-free A-B tree, these 2 flavors of that data structure have the exact same search code and the exact same data layout. Well, not the exact same data layout overall, just the data structure itself has the same data layout. So this just screams to me false sharing, the fact that there's such a huge performance difference that we're running the same code on the same data. So how do we find false sharing like this? Well, I'm going to show you how to use the Linux Performance Tools perf utility. And the idea is we're going to record a CPU performance counter. This is the counter. I'm not going to go into detail on exactly what this is, but roughly speaking, you can think of this as capturing memory contention. So here are the commands I'm going to run. I'm going to run perf record on my program. The -e CPU/event stuff is just specifying this performance counter that we're looking at. And perf record is going to record this performance counter while my program is run. And then I'm going to run perf report to analyze the output of perf record. So here's what perf report looks like. And it's telling me that about 93% of my memory contention happened in this function called thread timed. The name of the function is a little bit mangled because it's a C++ function. And we can press enter on this to drill in and actually annotate the assembly code, which has some lines of source code written alongside it so we can understand it, to see exactly where this memory contention is happening. And we can see 58% of the memory contention is happening at accesses to this global variable called start time. And about 41% of our memory contention is happening at accesses to this global variable called done. So what are these variables? Well, here's the code that's being executed by each thread in the test harness. While we're not done, increment the count of operations that I've completed. If I've completed a multiple of 50 operations, then get the current time. So I'm amortizing the cost of fetching the time. It's an expensive operation. I'm amortizing it over each 50 operations. And I subtract from the current time the start time to figure out how long I've been running. If I've been running for 3 seconds, then hey, set done equal to true and issue a memory fence so everyone else sees it, and then exit the loop. Otherwise, we're still going, so perform a random operation and then continue to the next iteration of the operation loop. So here's the offending data layout. Start time and done are globals that are declared one after another. Right before those two, we have an array called RNGs. This contains per thread random number generators, and each RNG has 8 bytes of data followed by almost 2 cache lines of empty padding to try to avoid false sharing. So I kind of thought that this data layout looked like this. You have an RNG padding, and so on, all the way up to the end where you have padding and then start time and done. And I sort of thought, well, this padding should prevent any false sharing between the RNGs and start time and done. And we shouldn't really have any false sharing between start time and done because start time is just written once at the beginning of the execution, and done is written to at most once per thread at the end of the execution. So any false sharing on those should not really be a factor in performance. And yet, we see lots of false sharing. We see a huge impact on performance, and perf tells us this is where the contention is. So after tearing my hair out and getting to the point where I start to question everything and all of my choices in life, I decided to finally just print the addresses of these variables and see where they were in memory. And that's when I realized my compiler was reversing the order of my globals. So we ended up with false sharing between done and start time and the first thread's RNG. And this might be kind of surprising to you if you know something about the C standard, which says that if you have variables in a struct, no compiler can reorder those variables. And yet this is not true for globals. Clearly compilers can and do reorder your globals, and who's to say how another compiler would reorder these things if it would. So what's the solution to this problem? Well, I could just add padding in between these two, exploiting the fact that my compiler is reversing the order of my globals. But that is kind of a brittle solution because that wouldn't necessarily work on another compiler. Or if I made some code tweaks, maybe it would rearrange things differently for some reason. So what's a non-brittle solution? Well, I hinted at it with the C standard comment about structs. You can't reorder the fields of structs as a compiler, so we can abuse that or just use that. Store all of your globals in a single global struct G, and the problem's basically solved. We can pad the beginning and the end of the struct and add padding throughout wherever we need it to avoid false sharing, and then we know exactly what the memory layout of our globals will be. So how does this impact performance? Well, it actually improves performance quite a bit, as the red bars here show. However, there are still some pretty big performance differences. Using the same techniques I just showed you, I dug through the code and ended up finding a bunch more instances of false sharing. I fixed those and the results look more like this, but we're still left with a couple performance differences to explain. So I don't have time to explain all of them. I actually have explained all of them to myself, but I don't have time to talk about them all here. But just to give you a flavor for what I mean when I talk about really explaining results, I do want to explain one more of these differences. I want to show why the lock-free skip list, just give a real explanation for why the lock-free skip list does so poorly compared to the other two. The other algorithms. So why is the skip list so slow? I'm going to use another tool, a C library called Pompey, stands for the Performance Application Programming Interface, to investigate this further, just to get kind of like a broad strokes description of where we're having performance problems. This library gives you the same kinds of measurements you would get with perf, except it's something you can use programmatically in the middle of your program, so you can do all of your setup and initialization and pre-filling of your data structures, and then start recording with Pompey. And then you can stop recording with Pompey before you do any deconstruction and teardown and destruction and finalization of your test harness. And then another nice thing is you get these results programmatically from Pompey, so you can actually divide the numbers you get by the number of operations that are completed by all threads to get more useful metrics. For instance, L3 cache misses per operation, cycles per operation, instructions per operation. And so here we have the results for the lock-free skip list and for one of the flavors of the lock-free BST that performed really well. And the really big glaring difference here is that the lock-free skip list performs a lot more instructions per operation. And this is sort of visible in our runtime as cycles per operation. So now that we have this sort of broad strokes idea of where this extra computational cost is coming from, we can use perf to dig deeper and get sort of the line numbers where this stuff is happening. So we use perf to dig into the CPU cycles to see where they are distributed throughout the program. And we see that the skip list search function spends about 20% of the total cycles of a whole trial just initializing these two arrays at the beginning of the search. So we have an array of predecessor pointers and an array of successor pointers for the current node that are maintained as we traverse the list. And just initializing these to contain all zeros takes about 20% of our total cycles. Digging a little bit more, we can see that there's a loop that iterates from the top level of the skip list down to the bottom. Remember, in a skip list, we iterate not only left to right, but also top to bottom. And the funny thing about this skip list implementation that I found was that the skip list max level is hard-coded to 20, and we're always iterating from the max level. So in some sense, the initial max level is also 20. And so in this loop, even though the skip list is empty and we just have a head node, we're still iterating 20 times from the top of the list down to the bottom, and that ends up burning somewhere between 15 and 20% of our cycles. So a lot of people would stop here. This sounds like an explanation, right? But to me, this is only a plausible explanation. This just leads to a hypothesis. The hypothesis is that it's because we have this huge initial max level in the skip list that we're getting all these slowdowns, because we're wasting all of this time. But I want to know exactly how much of a difference that makes, so I understand, are there any other performance factors affecting this? Is this a complete explanation? And so what I'm going to do is I'm going to construct an experiment to test that hypothesis, and it's pretty simple. I'm going to flatten the skip list. I hard-code the max level to 1. This really only makes sense because we're talking about an empty data structure workload, but we can do that, and running this experiment, we can see that that actually does account for basically all of the performance difference. So here, when we took it beyond a hypothesis to something that we actually tested, we've actually learned something really valuable. We have something we actually know for sure, not just something that we've conjectured. And so this is the approach that I would recommend everyone who does experiments in data structures follows, because now you have something that you can really say with certainty. Someone's not going to come along and overturn your explanation. So I mentioned that padding to fix false shearing can also be a double-edged sword. Here's an example of problematic padding. So this is a test harness and data structure that I got code for recently, and I was asked to take a look at it because the authors couldn't figure out why it wasn't scaling very well, why it wasn't reaching a very good absolute throughput. And I looked at their code and I realized that they were padding pretty aggressively to avoid false shearing. They were really afraid that false shearing would happen, but there was no real reason to suspect that there was going to be heavy false shearing on nodes. And by adding all of this padding, they ended up blowing up the sizes of nodes so their data structure didn't fit in cache very well. And so the penalty that they paid for exceeding the cache size was so much more severe than any, the cost of any false sharing that they would have incurred, that just by removing that padding, I was able to increase the performance of their algorithm by like more than 5 times and really help its scaling. So when you try to pad data structures, you have to, do a little bit of work to see if your padding is actually helping. And I would also recommend taking it a step further and trying to understand if it's helping, why is it helping? The last thing I'm going to talk about in terms of problems I see is a little bit more subtle. We're going to talk about memory layout anomalies that affect the performance of data structures. So this comes out of a work that I did with Adam Morrison and Maya R.A.R.E, where we took 10 data structures that are published in the data structure literature, and we really tried to drill down and understand exactly where the performance differences between these data structures are coming from, and to try to understand if the performance differences that people talked about in the literature actually exist, and if they exist, what are they actually caused by. So here are 2 data structures excerpted from that. We have an external lock-based BST, and we have an internal lock-free BST. The experiment here, we have 48 threads. We pre-fill the trees to contain 1 million keys each, and then we do 100% searches with a key range of size 2 million. And a couple of facts here. The external lock-based BST uses more nodes, and it has a higher average node depth, so path lengths are longer. The internal tree, of course, is shallower and uses fewer nodes to encode the same keys. And if you look at the search code for these two, the internal lock-free BST has a really efficient search code that looks really just like a sequential search in a BST. And the external one has some additional overhead. It has to touch locks and things like that. So we would really expect that the internal lock-free BST should be faster. So here, digging into these performance numbers a little bit to figure out where these performance differences are coming from, using Pompey I can see that there are more L2 and L3 cache misses for the internal lock-free BST. And this is really strange because, as I said, the external BST contains more nodes, so less of it should fit in cache, and that should translate into more L2 and L3 cache misses. But we see the opposite here. And so we dug a little bit deeper and we started to look at the actual layout of nodes in memory. So we looked in particular at how nodes were allocating, how threads were allocating nodes. And threads in the external tree would allocate nodes consecutively in memory. So they would go node, 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 node. The distance between 2 consecutively allocated nodes was exactly the size of a node, 64 bytes, in this case the size of a cache line, of course except where we cross page boundaries. Now, in the internal lock-free BST, this was not true. The internal lock-free BST allocated in its insertion operations not only a node, but also a descriptor object that describes the insertion operation to facilitate lock-free helping. And this descriptor object actually turned out to be about the same size as nodes. And so what happened was the allocator would interleave these allocations. So you had node descriptor, node descriptor, node descriptor. They were each about a cache line in size, and so they fit into the single cache line size class that was used by the allocator. And so the distance between 2 consecutively allocated nodes was 2 cache lines, size of a node plus the size of a descriptor. So what did this do? Why did this cause such a big performance difference? Well, if you remember I mentioned earlier, there's an adjacent line prefetcher in modern Intel processors. Whenever you load one cache line, it loads the adjacent cache line into the cache. And so every time a node was loaded into memory, the adjacent descriptor was loaded into memory as well. And these descriptors, although they were useful to facilitate helping when there are updates in progress, they are not actually used by searches at all. So this had the effect of halving our cache capacity that could be used to store nodes. And so of course this data structure ended up running much slower since it had half as many nodes in the cache. So we fixed this problem by padding descriptors slightly so that they were bumped up into the next allocator size class, so the allocator no longer interleaved them with nodes. And that affected the performance this much. So now this data structure was faster than the external one for searches, as we expected. And I want to point out, if we didn't consider a 100% search workload, then we might not have thought of doing this. You know, if we did like a 50% insert, 50% delete workload, we might have just said, oh, well, it has more cache misses. I guess the lock-free updates are more expensive. I guess that's what's going on. You know, memory system effects. But of course, that's not a real explanation. By going with a 100% search workload, we were able to say a priori, hey, I think this should be true. We were able to reason out some hypothesis and then challenge the results when they challenged our expectations. So I think that's a really valuable approach, and I encourage you to look really carefully at memory layout anomalies. So finally, let's look at my top 10 sanity checks. 5 of them are about correctness and 5 of them about performance. In the correctness category, I think you should run every data structure and every test harness you have through valgrind, and if you can't pass without any errors and with no memory leaks, then you got to fix up your data structures and test harnesses and try again. You should use key checksums. So the way you do this is you have each thread maintain a checksum, which is equal to the sum of keys that thread has inserted into the data structure minus the sum of keys it has deleted. And at the end of a trial, the sum of all checksums over all threads should be exactly equal to the sum of all keys in the data structure. If that's not true, then you have some sort of bug, you have incorrect updates, you have a non-linearizable execution. And this is really great for finding bugs in your implementations when paired with extremely high contention workloads. So look at extremely high contention workloads, you know, have 48 threads hammer a tree of size 100 with updates. Have them hammer a tree of size 10 with updates. Just get those really high contention workloads because they're really great at teasing out concurrency bugs. When you do your experiments, you're probably going to want to have a really nice, efficient memory reclamation scheme. Maybe you'll use this technique where you, when you get nodes to the point where they're safe to be freed, you sort of batch them together and free them at once to streamline your calls to the allocator. I would encourage you to have a bit you can flip in your test harness where you can switch between that kind of reclamation and eager reclamation, where as soon as it's safe, as soon as you think it's safe to free a node, you immediately free it. Because this will help you tease out bugs related to premature reuse of nodes and incorrect memory reclamation schemes and incorrect integration of a data structure with the memory reclamation scheme and so on. So it's really great for trapping these kinds of bugs. If you're working on lock-free data structures, I would also encourage you to try inserting artificial delays. You know, have threads go to sleep at key times, because you can lengthen windows where algorithms are kind of vulnerable to funny synchronization problems. You can prompt lots more helping. This is really useful for teasing out bugs. In the performance category, you should take variance measurements. In basically all the experiments I've ever done, I've been able to get my variance measurements pretty low. For example, I'm usually able to get my standard deviation within 5% of the mean for like 97% of my measurements. And in my experience, if you can't get your variance measurements low like that, then you almost certainly have an error in your configuration or some bug in your implementation, something you need to resolve. As you've seen, empty data structures and read-only workloads can be really helpful for tracking down false sharing issues. And of course, in the previous slide, we saw that read-only workloads can be really useful for tracking down memory layout anomalies. In the same vein, I think it's nice to look at object addresses. So just for each thread, for each object type, print out the first 20 or first 100 allocations, the addresses of the first 100 allocations for each object type, and just take a look at them. Are they spaced out as you expect? Is the distance between two objects the size of an object? Are they interleaved with other objects? This can give you a lot of insight into where performance differences might be coming from. Certainly something you can test with some auxiliary experiments. And last but certainly not least, I would encourage you to try running experiments on very large data structures. I think in the data structure literature, we're sometimes guilty of only considering experiments in which everything fits in cache or most stuff fits in cache. And ultimately, in the grand scheme of things, that's not a very realistic scenario, because if your data structure is used in the context of a larger program, a lot of the cache is going to be used by other program data. So you're only given a small slice of the cache. It's very unlikely that your data structure fits in cache. So if you don't do this and you just look at things that fit in cache, it's very easy to draw misleading or totally incorrect performance conclusions and to infer that certain algorithm designs are preferable when really in practice they wouldn't be. So take a look at those. In conclusion, I want to invite you to join me in performing R.A.R.E experiments. And if I could leave you with one point at the end of this talk, it would be really explain everything. Construct experiments to help you confirm everything. When you know absolutely beyond a shadow of a doubt that you actually have the correct explanation, not only that somebody else isn't going to come around and just totally overturn your results at some point in the near future, but also it helps raise the standard in the literature, and it leads to hopefully a body of experimental work that researchers will be able to trust and will be able to meaningfully build on. I want to mention briefly that in ongoing work with Adam Morrison, we're working on a new C and C++ test harness with a lot of tools to try to make it easier to produce these kinds of R.A.R.E data structure experiments. So here's a list of interesting features that we're trying to incorporate. So watch out for that. And I'm also working on a new tutorial series, how to do these kinds of R.A.R.E experiments in a lot more detail, walking through the tools and so on. The goal is to provide a resource that you can send your new grad students to, if they want to do experimental work. So hopefully they can learn from 10 years of my mistakes. And with that, I want to conclude the talk. Thank you very much, and I'll see you next time.